All right, good morning, guys. Can you guys hear me all right? Can you guys hear me okay? All right, cool. So we'll just kind of get going and people can join in if they show up a little bit late. I guess my general plan for this morning for both this period and the second period class at 11, if anyone wants to join that one also, is just to start off by just answering any general questions you guys might have, or any questions off of specific problems that you've been going through. And then if there aren't that many of those questions, then I'll probably just start going through some of the questions that I sent out last night that were those ones the College Board had posted that were extra practice problems. So got those ones up and ready in case we run out of other questions from you guys. So does anybody have any general questions or questions specific to any problems that you've been looking at? Sure, Natalie. Yeah, let me. We got a couple people here trying to get in. Let me let them in, and then we'll go over those questions you just asked about. So, you guys can see. Hopefully, it's just a blank screen now. Is that right? Okay, cool. Okay, so we'll start with your question, Natalie, from the stuff that I put on the review sheet about the intermediate value theorem. So basically all the intermediate value theorem is saying is that if I've got a function and that function is continuous on an interval from A to B, then any value that we pick, any W, for any W that is on the interval from f of A to f of B, there must be value C on the interval from A to B such that if you plug in C to your function, you get W. So that's the intermediate value theorem in its sort of basest form. And I was reading some more of the stuff, and it says they don't have any problem if you abbreviate IVT or MVT or extreme value theorem or any of those things. You can abbreviate all those with just IVT or EVT or MVT. So what it's saying is that on the range of y values, any y value that you choose between, suppose this is 2 and 10, I could pick 6. Then I know that somewhere between A and B, there's a value that when I plug it into my function, I get 6, or I get this W value, no matter what. And that's only true if f is continuous. F is continuous on the interval from A to B. That's what the intermediate value theorem is saying. And oftentimes they'll ask you this like on a chart or something, where they'll just, they'll give you something like, here's x and here's f of x, and they'll say, 1, 2, 4, and 7. They'll put some numbers in here like -2 and -1, 5, and 6, let's say. And they'll ask if it's guaranteed, if f is continuous, they'll say, is it guaranteed that there's an x-intercept on the interval 2 to 4? And well, the answer is yes, because 0 is where there'd be an x-intercept. And from 2 to 4, f of x goes from -1 to 5. Since f is continuous, it must have hit 0 in there. Or if they asked you, is it guaranteed that there's an x-intercept between 4 and 7? Well, the answer is no. But if it asks, will f of x attain the value of 5.5 somewhere between 4 and 7, the answer would be yes. Does that make sense, Natalie? For the intermediate value theorem? Okay. Anybody else have any other questions on the IVT? Yeah, I've got it recording, Juliana, so hopefully I'll be able to put it up there also. The last one seemed to work. I can't promise that this one will, but hopefully it will. All right, anybody else with a question on the intermediate value theorem? Correct, Tina. Yes, has to be continuous on that closed interval. Okay. And then Natalie, your next question was on the mean value theorem for integrals. So the mean value theorem for integrals is just that the average value, we'll say that the average value of any continuous function is equal to 1 over b minus a times the integral from a to b of f of x dx. So that's the basic formula for the mean value theorem for integrals. It's just 1 over b minus a times that integral from a to b. And so if we have a function like this, and we want to find the average value of it from a to b, the average value of it is some place in here where we would say that, that wasn't a very good example. Let's say that the average value is here, where the area of this rectangle is equal to the area underneath the curve. So the area of the rectangle, we'll call that h, is our average value. The area of the rectangle is equal to the area under the curve. So we've got b minus a times the height, h, which is our average value, should be equal to the integral from a to b of f of x dx. And so the way we get h, that average value, is we just divide by the b minus a. And that gives us this formula up here. Any questions there on the mean value theorem for integrals? It'll just ask you what's the average value of a function on this integral, or on this interval, and you'll just plug it into that formula. And you just have to know that it has to be a continuous function. All right, and then I think, Natalie, the last thing you were asking there was about secant line approximations. So if we've got a function that's concave up, and a secant line is just a line that goes through 2 points of that function. And so sometimes they'll ask you to write the equation of the secant line. So they'll give you the points, or you can find the points by knowing what x values and knowing the function itself. And so if you write the equation of that, you'll have, I have 2 points, so you'll use the slope formula to find the slope of your secant line. This is, well, wait, yeah, we'll just call this x1, y1, and x2, y2. And once you have the slope, you can plug it in. Y minus y1 equals your slope times x minus x1 into your point slope form. And so then you can use this secant line as an approximation for the value of the function also. Every once in a while, they'll ask you to do this. And when you do that, the important thing that you have to remember is that if you use a secant line to approximate a function that's concave up on this interval, so let's say this is from A to B, on A to B, let's say we were approximating this value, well, the secant line's approximation of this value would always be above if we were on a concave up function. But if it was a concave down function, then suppose we're trying to figure out this value, well, our approximation will always be an underestimate if the function's concave down. It's the opposite if you're doing it with a tangent line. If you're doing it with a tangent line, then the approximation at any value on here would be slightly below for a concave up function, and for here, the approximation would be a little bit above the actual value of the function. Does that make sense to everybody? Any questions on that? Natalie, does that answer your question? Cool. All right, I think Tina, you asked something about L'Hopital's rule. Let me scroll back up here and see what you said. When do you know not to use L'Hopital's rule? You mean when you have an indeterminate form and when not to use it, even if it's still 0 over 0 or infinity over infinity? Is that what you're asking, Tina? Okay, I don't know. She's not answering. Oh, there we go. Okay. Yeah. Okay. So yeah, sometimes it is more time consuming. So if it's easy enough to take the derivatives, do it. But sometimes you might end up with something like, and usually the only cases of this are when it's like kind of nasty trig functions. So if we're looking at the limit as x approaches 0 of something like sine to the 4th of 3x squared over x to the 8th. If we plug in 0 to this, it's 0 over 0. And we could take the derivative and use L'Hopital's rule for this. But you'll note that every time you take the derivative of this x to the 8th term, you're going to end up with 8x to the 7th. And that's still going to be 0 in the denominator. And every time you take the derivative of something like sine to the 4th of 3x squared, if we take the derivative of that, it's 4 sine to the 3rd of 3x squared times cosine of 3x squared times 6x. And when you plug in 0 for x into this, you're still going to get 0, but partly because of the 6x and partly because of this 4 sine cubed of 3x squared, they're both equal to 0. So you're still going to end up with 0 over 0, and you're going to have to just keep repeating derivatives, and this numerator's derivative is going to get horribly, horribly complicated. I mean, even the second derivative is going to be really complicated. So you're not going to want to when you have trig functions that look like this. So a better option for you there is to try to turn it into the form of sine of x over x. And so we can say that really what we've got here is a limit as x approaches 0 of the sine of 3x squared being raised to the 4th power over x squared being raised to the 4th power. And we can pull the power of 4 outside of everything. And all we need to do then is put in a 3 down here. And so if I put in a 3 down here, that means I've got to put in a 3 up here also. And it's really a 3 to the 4th power, and this is really a 3 to the 4th power. And so this 4th power comes around everything, and then this 3 to the 4th, which is 81, comes out in the front, and you have the limit as x approaches 0 of the sine of 3x squared over 3x squared, all raised to the 4th power. And using a simple u substitution, which you don't even need to show on the test, that this limit here inside of there is equal to 0. So you've got 81 times 0 to the 4th, which is just 0. Does that make sense, Tina? Cool. Any other questions on this particular problem? And then I'll answer your question, Kiana. Anybody else have a question on this one? Correct, Seth. Whenever you use L'Hopital's rule, you need to write out that you used L'Hopital's rule. And as I was looking through their guidelines, it says you can abbreviate things like the intermediate value theorem and the fundamental theorem of calculus and the mean value theorem. It didn't specify that you could abbreviate L'Hopital's rule, so write the whole thing out. Just write using L'Hopital's rule and then continue on. Don't abbreviate with just the LH. Okay, Natalie, the ones that you should just have memorized, I should have put those on that review sheet now that I think about it. I'll add these to it. Limit as x approaches 0, sine x over x is 0. Limit as x approaches 0 of tangent x over x is 0. Limit as x approaches 0 of x over sine x is 0. Limit as x approaches 0 of x over tangent x is equal to 0. And the limit as x approaches 0 of 1 minus cosine x over x is equal to 1. Those ones would be good ones to know. I'll put those on the sheet just in case you forget. But I'll do that sometime today and resend that paper out. Oh, geez. Yeah, I wrote all those backwards. Wow, sorry. It's my fault there. Wow, sorry about that, guys. All of those. I don't know why I did that. That one is 0, and all of these ones are 1. I'll put the right things on that review sheet. I think I just did that over here too. Yeah. This should be 1 to the 4th, which ends up giving us 81 for this. Sorry about that. Thank you, Ryan and Molly. I don't know what I was thinking there for a second. I'm glad somebody corrected me on that. Everybody good there? Okay. All right, so yeah, Tina, nothing that requires a calculator will be on the test. Linearization doesn't necessarily require a calculator. Linearization is just using a tangent line to approximate something. So it could be on there, but it's just in the form of a tangent line approximating things. Okay, so Kiana, you were asking for number 1 of the College Board's second practice exam F, which was a limit thing. So I think the second practice exam 1F, that was this one here, right? Okay, so we'll need a little bit of context here as we go through this. Hopefully you guys have all looked at this problem already, but it's telling us that we know that the limit as x approaches 5 of g of x can be evaluated using L'Hopital's rule, which means that we know that this should come out to be 0 over 0 when we plug in 5 to it. And so we've got, if we plug in our 5 here in the numerator, we've got 5 plus cosine of 5 pi over 3 minus the square root of f of 5. And cosine of, sorry, not cosine of 5 pi, but just the cosine of pi. And cosine of pi, 5, I didn't put my 5 out there, 5 cosine of pi. And our cosine of pi is -1. And so this becomes 0 over 3 minus root f of 5. And so in the problem, they're asking us to find f of 5. Well, that's just telling us that since we know that this can be evaluated using L'Hopital's rule and the numerator is 0, that the denominator must also be 0. And so we just need to solve for f of 5. So we'll bring it over to the right-hand side and then square both sides. That'll give us f of 5 is equal to 9. Does that make sense for the first part, Kiana, of that, to find f of 5? Or for everybody? Anybody have any questions on finding f of 5 there? Okay. And then it wants us to also find f prime of 5, which means that we need to take the derivative of the numerator and the derivative of the denominator here. So we're looking now at the limit as x approaches 5 of the derivative of the top. So the derivative of the top is 1, and then 5 cosine of 1/5 pi x. That should become, when you take the derivative of that, minus, and then the 1/5 pi comes out into the front times the pi, which is pi sine 1/5 pi x over, and then this denominator, the 3 goes away, and the derivative of negative square root of f of x should become -1 over 2 root f of x times the derivative of f of x, which is f prime of x. And so that's going to help us to figure out what f prime of 5 is in a second here. But first we'll plug in 5 to everything and evaluate all the stuff that we know. So we've got 1 minus pi times the sine of 5, 5/5 or 1 pi. And so that's going to give us just 0, 1 minus 0 up there. And the denominator, we already found f of 5 to be 9, so the square root of 9 is 3, times the 2 is 6, so we got -1/6 f prime of x down here. And so let's let me clear this off here so I have a little more room. So from there, actually, let's put that back. I'll just continue this up at the top. From there, we have to go back and look at some of the other work that we would have done in other parts of the problem. So it's telling us that we're looking for the limit as x approaches 5 of g of x. And so hopefully you've already worked through this problem, but we know that g of 5 is equal to 1. And since this is a differentiable function, since g is differentiable, and we know that g of 5 is equal to 1, so we're gonna say g of 5 is equal to 1, and we know that this is a differentiable function, and if a function is differentiable, it means that function is continuous. And the definition of continuity says that if a function is continuous at all real numbers, then at every point, the limit as x approaches 5 of that function, which is what we're looking for, should be equal to g of 5. So we know that this whole thing here, 1 over -1/6 f prime of x, needs to equal 1. And so from there, we should be able to solve that out. We just multiply by the f prime of x, and 1 divided by -1/6 gives us f prime of x is equal to -6. Or it's f prime of 5, but f prime of 5 is equal to -6. Should have made that 5 earlier, but any questions on that? And that one's a little complicated. Does that make sense, Kiana? and everybody. Any questions on that? Yeah, you should show the chain rule there for the, I mean, you don't need to like write it. You don't need to write out the chain rule. You just need to, you just need to take the derivative itself and write out what the derivative is. So whether you need to write out the chain rule or not, that's up to you. But they don't care if you show the steps of the chain rule explicitly, as long as your derivative is correct. Let's see, Justin, are we allowed to use sites like derivative calculator on the test? Yeah, so, I mean, I can't imagine that they're going to give you anything that's really going to require you to take any difficult derivatives, because obviously they know that people can just look up the derivatives of things. And so it doesn't seem, it doesn't seem like that's something they're going to do. I mean, I wouldn't want to say, use the derivative calculator website to calculate them, because that seems like you shouldn't do that, but I'll leave that up to you. Any other questions so far on anything? Any questions on this problem that we just did, or anything we've talked about, or any other questions you want to bring up? Yeah, we can do part E, Arthi. Let's see here. Let me give me 1 second here. Let me put this on a new page. So we can see a little better here. So we're looking at our function m of x, which is the derivative of the integral from 0 to 2x of g of t. And we know that c equals 2.5 satisfies the conclusion of the mean value theorem for this on 1 to 4. And we're trying to find out some other stuff about g of 8 minus g of 2. So let's kind of take this step by step. First of all, if we know that it satisfies the conclusion of the mean value theorem, that means that m prime of 2.5 should be equal to the average rate of change, or the slope of m, so m of 4 minus m of 1 over 4 minus 1. So that's the sort of the base part of the mean value theorem that it's having you start with. So then we need to figure out what is m prime and what is m of 4. It's quite possible, Cody, that we might need to. I don't remember what was D. Let's see, part D was writing an expression for m prime. Yeah, so yeah, to find m prime of 2.5. Yeah, so yeah, we're going to find m prime of 2.5 right now, which was part of part D, or which was all of part D. So to find m prime of 2.5, we need to take the derivative of this. So first off, m of x is the derivative of the integral from 0 to 2x of g of t. So m of x should be, we just plug in 2x and we multiply by the derivative of the 2 using the chain rule. So m of x is 2g of 2x, and m prime of x then should be 2 times the derivative of g of 2x, which is g prime of 2x, times the derivative of 2x, which is 2. So that's 4 g prime of 2x. And if we're looking for m prime of 2.5, that should then be equal to 4g prime of 5. Kiana, it's 2g of 2x because when you take the derivative of an integral from a constant to a function, it just becomes the original function evaluated at this upper limit times the derivative of this using the chain rule. It's like doing a simple u substitution. So the derivative of the integral from 0 to u of g of t dt with u equal to 2x. And so the derivative with respect to x of this should be g of u times du dx. And so g of u is g of 2x, and then du dx is 2. That makes sense, Kiana? Yeah, okay. All right, so we're now looking at m prime of 2.5 is equal to 4 times g prime of 5. And so let's see here, g prime of 5, I'm sure they gave us something about that, or we already found that some way or another in the problem. Let's go back here and take a look. So looks right here. Part A was to find g prime of 5. 1 second here. Okay, sorry about that. Can you guys still hear me? Okay. All right, so to find g prime of 5, we know that this line right here is tangent to g at x equals 5. So g prime of 5 should just be whatever the slope of this is. So g prime of 5 should just be negative 5/3 because the slope of the tangent line is that value. So we'll take that value from A and say that this is equal to 4 times negative 5/3 or negative 20/3. So now what we're looking at here is negative 20/3 is equal to, I believe it was m of 4 minus m of 1 over 4 minus 1. If we look back to what we had written originally up here, m prime of 2.5, which you've now found, is m of 4 minus m of 1 over 4 minus 1. And we can get rid of the 3's there. So we got negative 20 is equal to m of 4 minus m of 1. And from there, we know what m of 4 here is and what m of 1 is because we know how m and g are related here. M of x, and we'll do this on this page here. From this, m of x is equal to the derivative of the integral from 0 to 2x. So like we said before, m of x is equal to 2g of 2x. So we'll go back over here and say that negative 20 is equal to 2g of 2 times 4 minus 2g of 2 times 1. By doing that substitution, this gives us negative 20 is equal to 2g of 8 minus 2g of 2. We can take the 2 out of that, and it asked us to find g of 8 minus g of 2. So all we have to do is divide by the 2 to get negative 10 equals g of 8 minus g of 2. That's pretty long and complicated one there, but hopefully that makes some sense. It would have been a little quicker if we'd already done all those other parts previous to it. But any questions there? All right, other questions that you guys might have. Okay, Dylan, you want me to go over the extreme value theorem. So the extreme value theorem just says that if you have a function that is continuous on a closed interval, okay, then that function must have, let's say f is continuous on closed interval a to b, then there must be, f must have an absolute max and an absolute min on the interval from a to b. That's what the extreme value theorem is saying. And so one possibility is that absolute minimum could be at an endpoint, like this one has a as the endpoint, and that's the absolute minimum on a to b. Or it could be that the maximum is at some interior point, or perhaps I'd drawn this a little higher, the maximum could be at an endpoint. But it guarantees that there is an absolute max and an absolute min on the interval. And one of the important things we have to remember with the extreme value theorem then is that if it asks you for an absolute max and an absolute min, this is why I always say if you have a closed interval, you have to check the endpoints, because the max and the min might not necessarily be at interior points, but it might be at the endpoints as well. Does that help, Dylan? Cool. Anybody else have questions there on the extreme value theorem? We got, let's see, Justin, does the sandwich theorem just guarantee that the limits of all three functions as they approach an x value are the same? Or does it guarantee that the values of all three functions at that same are the same at that one x value? Yeah. So the sandwich theorem says that, so we'll quickly go through here. The sandwich theorem is saying that if you've got functions, and I know there was a question in there, in one of those practice problems that they gave you guys about this, that if you have one, if you got one function that's sandwiched between two other functions, that it tells you that the limit as x approaches a of, we know that the limit as x approaches a of f of x equals c, and we know that the limit as x approaches a of h of x is also equal to c. The only thing that it specifically tells us is that the limit as x approaches a of g of x is also equal to c. But we can infer from that, if it says that these are all continuous functions, that the values of f of a and g of a and h of a must all equal c, but only if they're all continuous at the point c. So these, the sandwich theorem or the squeeze theorem doesn't initially indicate that it has to be continuous at this, continuous at a, not continuous at c, the point we're approaching. If these are continuous at a, then the values must also be the same. But any number of these could be undefined at x equals a and still have the limits equal to each other. Does that make sense, Justin? Okay. Molly, finding horizontal and vertical asymptotes. So yeah, a horizontal, if you're talking about horizontal asymptotes are just the limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. And so, I mean, you just need to evaluate those limits for whatever function you're given. If it's a rational function, we know that the limit as we approach infinity and the limit as we approach negative infinity will be the same. But if it's not the same, if it's not a rational function, then we don't necessarily know that. And one of the things that I put on that sheet was we have something like the limit as x approaches infinity of the square root of x squared plus 1 over 2x, and the limit as x approaches negative infinity of the square root of x squared plus 1 over 2x. And while they look very similar, when we know we're going towards infinity, so the 1 goes away and we just end up with the square root of x squared. Well, the square root of x squared is absolute value of x over 2x. And the same for this one. And then, since we know that x is going to a positive number, the absolute value of a positive number is always the same thing that you started with. So this one is the limit as x approaches infinity of x over 2x, which is just the x's cancel and it's a half. But down here, you're taking the absolute value of a number that's negative. And so this becomes the limit as x approaches negative infinity of, when you take the absolute value of a negative, you take the opposite of it. So it's negative x, or the opposite of x, over 2x. The x's cancel, and that one's negative 1/2. So be careful on ones with the square roots in them. 1 second, I got to take care of something real quick, and then I'll be right back to finish answering your questions. All right, sorry about that. My kid couldn't get into his Zoom meeting on his iPad, so I had to log him in on my phone to get him in for his class. All right, so any questions on that limit that we were just doing? Can you guys hear me all right? Okay, so any questions on this one with the horizontal asymptote? The horizontal asymptotes, everybody all right with that? Okay, let me scroll back up. So Kiana, you were asking about that last one on with the sandwich theorem, where they had you do the sandwich theorem one. I'll go back to that real quick. Let's see here. That was this one right here. We haven't done the whole problem, but it's basically what Justin was asking about a minute ago. So since we know, and it told us before that this function was that h and g were both continuous, we would just need to do the justification that the sandwich theorem tells us that those limits are all equal to each other, and if k, they're looking for whether or not k is continuous at x equals 5. And so since the sandwich theorem tells us that this limit was equal to, I don't know what the value was, but whatever that limit was equal to, and whatever this limit was equal to, yes, k must be continuous there also, because of the sandwich theorem that says that this limit must equal this limit must equal this limit. So that'd be enough. Just using the sandwich theorem as your justification is good there. I think somebody else had another question that I missed. Oh, Molly, I was going to answer about vertical asymptotes. So vertical asymptotes, I wouldn't imagine that you're going to have to worry much about vertical asymptotes unless it's on like a tangent function or if it's a rational function. So you know that the tangent function has asymptotes at negative pi over 2 and pi over 2 and 3 pi over 2 and so on. And that rational functions will have a vertical asymptote whenever the denominator is equal to 0, but the numerator is not also equal to 0. So if I have something like 2x minus 1 over x minus 2, you know, it's got a vertical asymptote of x equals 2. You can prove that by showing the limits as x approaches 2 from the left or the limit as x approaches 2 from the right of, we'll call this f of x, and they'll either be infinity or negative infinity. So in this case, if we plug in a value just to the right of 2, like 2.0001, we've got a positive in the numerator and a very, very small positive in the denominator. So this is infinity. This one with like 1.999, it's a very small negative, and it's a positive in the numerator, so it's a negative infinity. No, Molly, you don't have to show both if it was asking you to justify them using limits. I don't think they'll ask you to justify vertical asymptotes using limits, but one of them is sufficient to show it. Yeah. All right. Other questions? Anybody else have any questions at the moment? Oh. Can I do an example sandwich theorem, but not a super simple one? Let's see. I mean, the only one I know of that, I mean, I haven't seen any sandwich theorem problems on the AP test in recent years, except for the one that they just did last year. I mean, or that one that they've put up recently that we were already sort of talking about. Let me go back to this one. Yeah, I mean, I can't imagine that they're going to do anything that would be much different than what this is. Trying to think about something else that would work. Because we already talked about this one, sort of. Yeah, I mean, the only context that I can really think of that they might ask you a sandwich theorem question is where they give you something like something like, suppose f of x is equal to, let's say, x squared minus 1 over x minus 1, and h of x is equal to, let's go with sine x over x plus 1. And it says something like, it is known that f of x is less than or equal to g of x is less than or equal to h of x on, let's just say, the interval from negative point, or not negative, let's go positive 0.99 to 1.01, let's say. And it asks us find the limit as x approaches 1 of g of x. And so you'd have to know that you're using the sandwich theorem but you need to find the limit as x approaches 1 of f of x, which we can see from this. This is equal to, well, if we, this is equal to x plus 1 times x minus 1 over x minus 1. Those cancel out. That equals 2. And this, you'd want to show that the limit as x approaches 1 of h of x is also equal to 2. And so we would know, based on the fact that these limits are both 2, and that this function and this function sandwich g of x, that the limit as x approaches 1 of g of x will also have to equal 2. That's really the only context I can think of where they might throw something at you like that. They might give you some more difficult limits, but does that help, Molly? I don't know. Okay, good. All right, Kiana, an optimization problem that would be similar to a College Board problem. I haven't seen any of their recommended questions. None of them have included optimization problems. But let's see if I can come up with something here on the top of my head real quick. Let's say, shoot. Yeah, let me answer your question in a second, Kiana. You're right, Molly. That was a bad question I came up with just there. Now that you mentioned that, that's what happens when I try and come up with stuff sometimes off the top of my head. Let's pretend this function was, I forgot we were going to 1, not to 0 there. Let's pretend this function was x plus 1. Now that function is x plus 1, this should work. So, yeah. Sorry, thanks for pointing that out, Molly. Sine x over x wouldn't work on that, because only if we're approaching 0 is that equal to 1. Good point. All right, Kiana, let me try and come up with this optimization thing here for you. Suppose they gave us this, they might give us like a chart of values. Let's see if I can get something that'll work for this, where x is equal to 0, 1, 2, 3, 4. Let's call this like 10, 20, 25, 30, 20, something like that. And let's say that g of x was equal to x squared minus 1. And we said that h of x is the cost of manufacturing something, and h of x is equal to let's say that that's equal to g of f of x and nah, I don't like that. Let's say that it's equal to, actually let's kill this chart here. Let's just call f of x equal to x squared plus 2x plus 2. We'll see how this works. And we'll call this f of g of x still. I think that's what I just had a second ago, or maybe not. But and we want to know when is the cost at a maximum, let's say. So I could see them pulling something like this, where they might show where you need to figure out what f of g of x is and then find its derivative, or use h prime, which should be f prime of g of x times g prime of x, and set that equal to 0. So f prime is 2x plus 2, and we're going to plug in, we're going to evaluate that at g of x, and then multiply that by 2x. And so we'd end up with 2 times x squared minus 1 plus 2 all times 2x, which comes out to be, what does that come out to be? 2x squared minus 2 plus 2 is just 2x squared. That didn't turn out too great, but it came out to be 4x cubed. And we'd set that equal to 0 and say, well, the minimum cost or the maximum cost then could be when x is 0, or the minimum cost could be when x is 0. And then we'd have to look at a sign chart here to figure out if that's a max or a min. So if we plugged in a positive number into our derivative, which was 4x cubed, we get a positive. And if we plugged a negative in, we get a negative, and that would tell us that this was actually a min. And so we would say there is no max cost for this. That's something generally like that is kind of what they might do if they were going to do an optimization, where they give you a couple of different functions and have you find the derivative and do it that way. But that's all I can kind of think of for optimization. Does that sort of help, Kiana? Cool. I know the numbers didn't work out real great, but that's just kind of what happens when I pull them out of nowhere. Any other questions on anything or specific problems that you want me to do? Let's see, Ryan, when solving a differential equation, would you get marked off a point or two if you don't mention the interval of validity? No, unless it specifically asks on what interval is this valid or what is the domain of your solution, then you don't need to put it. If they specifically ask for it, then definitely put it. And if you don't, they'll mark you off. Molly, I can't imagine that they're going to have you do Newton's law of cooling. Just know that the thing to know about that is that it comes from a separable differential equation with exponential growth. But you don't need to memorize the formula for it. No, definitely not. Other questions? Anything else at the moment? All right, well, then we'll stop for a minute here, and I'll restart back up at 11 with the second period group. But like I said, you're all welcome to join again for second period if you want, and I'll answer any other questions that they have. And even if you were in